What if I told you there's a new weapon that can travel from New York City to Los Angeles in under 30 minutes? We're talking about speeds faster than 5 times the speed of sound. That's hypersonic speed. We're entering a new age of warfare, an age dominated by hypersonic missiles. These aren't your typical missiles. They represent a giant leap in technology. To understand the significance, we need to rewind a bit. For decades, nations have relied on ballistic missiles. These weapons travel incredibly fast, but they follow a predictable path. This predictability makes them vulnerable, easier to intercept. Hypersonic missiles change the game completely. They move at such incredible speeds that they render traditional defense systems almost useless. Imagine trying to hit a bullet with another bullet. That's the kind of challenge hypersonic weapons present. But it's not just about speed, it's about agility. These missiles can maneuver in flight, making them incredibly difficult to track and even harder to intercept. This combination of speed and maneuverability makes hypersonic weapons a game-changer in modern warfare. But how did we get here? What breakthroughs led to the development of such revolutionary technology? The journey to hypersonic flight has been a long and challenging one. Scientists and engineers have been fascinated by the idea of traveling faster than the speed of sound for decades. Early attempts focused on rocket-powered aircraft, pushing the limits of known technology. The sound barrier itself, once considered an unbreakable limit, was shattered in 1947. This breakthrough opened the door to supersonic flight, paving the way for advanced jet fighters. But achieving hypersonic speed, Mach 5 and beyond, proved to be a far greater challenge. The extreme heat generated by air friction at such speeds posed a significant hurdle. Materials would melt, and conventional engines couldn't handle the stress. It required groundbreaking advancements in materials science, propulsion systems, and aerodynamic design. New materials capable of withstanding thousands of degrees of heat had to be developed. Scramjet engines capable of burning fuel in a supersonic airflow emerged as a promising solution for hypersonic propulsion. These technological leaps allowed us to finally breach the hypersonic barrier and explore the possibilities of high-speed flight. The United States, recognizing the strategic importance of this technology, has invested heavily in hypersonic research and development. The result? The creation of cutting-edge hypersonic missiles that are set to redefine the future of warfare. These missiles are not just prototypes, they are operational weapons. The U.S. military has successfully tested and deployed hypersonic missiles, showcasing their capabilities to the world. The development of these weapons has sparked a global hypersonic arms race, with nations like Russia and China also pouring resources into acquiring this game-changing technology. The implications are profound, as hypersonic missiles have the potential to shift the balance of power on a global scale. They could render existing defense systems obsolete, creating new vulnerabilities and forcing nations to rethink their military strategies. In the world of international relations, the emergence of hypersonic weapons represents a paradigm shift, ushering in a new era of strategic competition and uncertainty. Join me as we delve deeper into the fascinating world of hypersonic missiles, exploring their inner workings, their strategic implications, and the global race to harness their power. Before we dive into the world of hypersonic missiles, it's essential to understand how we got here. The story begins in the midst of World War II with a technological terror, the V-2 rocket. Developed by Nazi Germany, the V-2 was the world's first ballistic missile. This revolutionary weapon, powered by a liquid-fueled rocket engine, could reach incredible speeds, soaring high into the atmosphere before crashing down on its target. While terrifying, the V-2's accuracy left much to be desired. It was more of a weapon of terror than a precision strike weapon. The end of World War II saw the dawn of the Cold War and an arms race between the United States and the Soviet Union. Both superpowers, recognizing the potential of rocket technology, poured resources into developing their own ballistic missiles. These weren't just bigger versions of the V-2. They were far more sophisticated, capable of carrying nuclear payloads across continents. The ICBM, or Intercontinental Ballistic Missile, was born. These weapons could travel thousands of miles, reaching speeds exceeding Mach 20, making them a terrifying deterrent in a world on the brink of nuclear war. Ballistic missiles, while powerful, had a critical flaw: their predictability. They followed a fixed parabolic trajectory, making their flight path relatively easy to calculate. This predictability made them vulnerable to interception, especially as anti-ballistic missile systems advanced. The world needed something faster, more agile, something that could outmaneuver these defenses. This need for speed led to the pursuit of hypersonic flight. supersonic dreams and challenges. The quest for hypersonic speed, Mach 5 and beyond, wasn't just about building faster missiles. It was about pushing the boundaries of what's possible. Early experiments with hypersonic flight focused on aircraft like the X-15, a rocket-powered plane that could reach speeds of over Mach 6. These flights provided invaluable data on the challenges of hypersonic flight, particularly the intense heat generated by air friction at such speeds. Imagine an aircraft traveling so fast that the air around it heats up to thousands of degrees, hot enough to melt metal. This extreme heat posed a significant engineering challenge. Overcoming this heat barrier required breakthroughs in material science. Scientists developed new alloys and composites capable of withstanding these scorching temperatures. The space shuttle, for example, relied on a thermal protection system made up of thousands of heat-resistant tiles to survive the fiery re-entry into Earth's atmosphere. These advancements in materials science laid the groundwork for the development of hypersonic vehicles, including missiles, that could withstand the extreme conditions of hypersonic flight. But heat wasn't the only obstacle. Hypersonic flight also meant dealing with shock waves, abrupt changes in air pressure that could create immense stress on a vehicle's structure. Engineers had to design new aerodynamic shapes and control systems that could navigate these turbulent forces. Wind tunnel testing became crucial, allowing engineers to study how air flowed around hypersonic vehicles and make necessary design adjustments. Advancements in propulsion. Achieving sustained hypersonic flight required more than just heat-resistant materials and aerodynamic designs. It demanded a revolution in propulsion systems. Traditional jet engines, while powerful, couldn't handle the extreme conditions of hypersonic flight. This led to the development of the Scramjet, or supersonic combustion ramjet engine. Unlike conventional jet engines, which use rotating blades to compress air, scramjets rely on their forward motion to force air into the combustion chamber at supersonic speeds. This unique design allows them to operate efficiently at hypersonic speeds using the very air they're traveling through as fuel. Developing a scramjet engine was no easy feat. It required a deep understanding of supersonic combustion, a complex process where fuel is burned in a supersonic airflow. It also meant overcoming technical challenges like cooling the engine and ensuring stable combustion at such high speeds. Despite these hurdles, scientists and engineers persevered, and scramjet technology gradually matured. The development of the scramjet engine was a game-changer in the pursuit of hypersonic flight. It provided a viable propulsion system capable of powering vehicles to speeds previously unimaginable. This breakthrough paved the way for the creation of hypersonic missiles, a new breed of weapon that would forever change the face of warfare. With advancements in materials science, aerodynamics, and propulsion technology, the stage was set for the emergence of the hypersonic missile. These weapons combined the speed of ballistic missiles with the maneuverability of cruise missiles, creating a formidable threat unlike anything the world had ever seen. Unlike ballistic missiles, which followed a predictable parabolic trajectory, hypersonic missiles could maneuver in flight, changing course to evade enemy defenses. This agility, coupled with their blistering speed, made them incredibly difficult to track and intercept. The development of hypersonic missiles marked a paradigm shift in military technology. They represented a new era of warfare, one where speed and maneuverability reigned supreme. These weapons had the potential to overcome even the most sophisticated air defense systems, giving a significant advantage to the nations that possessed them. The emergence of hypersonic missiles sparked a global arms race, with countries like the United States, Russia, and China vying for supremacy in this new domain of warfare. The stakes were high, as these weapons had the potential to reshape the balance of power on a global scale. We throw around the term hypersonic, but what does it actually mean? To understand the awe-inspiring capabilities of these missiles, we need to grasp the basic science behind their speed. Picture this, the sound barrier. It's not a physical wall, but a point where air resistance dramatically increases as an object approaches the speed of sound. Breaking this barrier was once considered unthinkable, yet today, we're talking about speeds 5 times faster. Hypersonic speed is all about Mach numbers. Mach 1 is the speed of sound, which varies depending on factors like altitude and temperature. At sea level, it's roughly 767 miles per hour. Hypersonic flight starts at Mach 5, or 5 times the speed of sound, and extends to speeds above Mach 10. To put that into perspective, imagine traveling from New York to Los Angeles in under an hour. But hypersonic flight isn't just about raw speed, it's about the unique physical phenomena that occur at such velocities. As an object punches through the air at hypersonic speeds, it creates intense shock waves, similar to the bow wave of a ship but far more powerful. These shock waves compress and heat the air around the vehicle, leading to extreme temperatures and pressures. This is where things get really interesting. At hypersonic speeds, the air surrounding the vehicle becomes so hot that it can no longer be treated as a normal gas. It undergoes chemical changes, becoming partially ionized and forming a plasma. This plasma sheath, as it's known, can disrupt radio communications and even affect the vehicle's aerodynamic properties. Riding the shock waves, the art of hypersonic flight. Designing a vehicle capable of withstanding the rigors of hypersonic flight is an engineering marvel. It's not just about building something fast, it's about creating a craft that can harness the very forces that make hypersonic flight so challenging. One of the key concepts in hypersonic vehicle design is wave riding. Remember those intense shock waves we talked about? Well, hypersonic vehicles are designed to literally ride these waves. By carefully shaping the vehicle's body, engineers can manipulate the shock waves, using their energy to generate lift and reduce drag. This wave-riding capability is what allows hypersonic vehicles to achieve stable flight at such extreme speeds. But hypersonic flight is about more than just going fast in a straight line. These vehicles need to be maneuverable, capable of changing course to evade enemy defenses or strike their targets with precision. This is where things get really tricky. At hypersonic speeds, even the slightest change in the vehicle's orientation can create massive aerodynamic forces. To overcome this challenge, hypersonic vehicles incorporate advanced control systems that make lightning-fast adjustments to the vehicle's flight surfaces. These control surfaces, often located on the vehicle's wings or tail, can deflect the airflow, generating lift, drag, or even rolling moments. These precise movements allow hypersonic vehicles to maneuver with surprising agility, despite their incredible speed. Building for the Inferno materials that defy heat. Imagine an aircraft traveling so fast that the air around it glows red hot. That's the reality of hypersonic flight. At speeds above Mach 5, air friction generates temperatures that can melt even the strongest metals. Building a vehicle capable of withstanding this intense heat is one of the biggest challenges in hypersonic technology. It's like designing a spacecraft to re-enter the Earth's atmosphere, but instead of a one-time event, it's continuous. To protect hypersonic vehicles from this inferno, engineers have turned to exotic materials and innovative design solutions. One of the most critical components is the heat shield, a protective layer that covers the vehicle's leading edges and other areas exposed to extreme temperatures. These heat shields are typically made from advanced ceramic composites, materials capable of withstanding temperatures that would turn steel into molten slag. But heat shields are just the beginning. The entire structure of a hypersonic vehicle must be designed to cope with extreme temperatures. This means using high-temperature alloys for the vehicle's frame and skin, materials that can maintain their strength and integrity even when subjected to thousands of degrees Fahrenheit. Engineers also need to carefully consider thermal expansion, the tendency of materials to expand or contract with changes in temperature. To prevent the vehicle from warping or buckling under the intense heat, they use special joints and fasteners that can accommodate these thermal stresses. In some cases, they even incorporate active cooling systems that circulate coolants through the vehicle's structure to help dissipate heat. We've talked about the challenges of hypersonic flight, but what about the engines that make it all possible? Achieving sustained hypersonic speeds requires a different breed of propulsion system, one capable of operating efficiently in the extreme conditions of supersonic combustion. Enter the Scramjet, or supersonic combustion ramjet, a marvel of engineering that literally breathes air at supersonic speeds. Unlike conventional jet engines, which use rotating blades to compress incoming air, scramjets rely on their incredible speed. As the vehicle blasts through the atmosphere, the air is forced into the engine's intake at supersonic speeds. This ram compression eliminates the need for heavy, complex compressors, making scramjets ideal for hypersonic flight. Once inside the engine, the supersonic airflow mixes with fuel and ignites in the combustion chamber. The expanding hot gases are then expelled through a nozzle, generating thrust. But operating a scramjet is no walk in the park. It's like trying to keep a blowtorch lit in a hurricane. The supersonic airflow through the engine creates intense heat and pressure, pushing materials and combustion processes to their limits. Despite these challenges, scramjet technology has made significant strides in recent years, thanks to advancements in materials, computational fluid dynamics, and combustion control. Researchers are also exploring alternative hypersonic propulsion systems, such as detonating engines that use controlled explosions to generate thrust. The other crucial factor is maneuverability. Unlike ballistic missiles, which follow a predictable parabolic trajectory, hypersonic missiles can zigzag, change course, and even glide, making them incredibly difficult to intercept. This agility stems from a combination of aerodynamic design, advanced control systems, and in some cases, the ability to utilize atmospheric lift. Imagine a missile streaking through the atmosphere at Mach 5, making sharp turns and sudden dives, all while enduring extreme temperatures and G-forces. To achieve this level of maneuverability, hypersonic missiles often incorporate innovative flight control surfaces, such as movable fins, canards, or even thrust vectoring systems. These control surfaces, strategically placed on the missile's body, can deflect the airflow, generating lift, drag, or rolling moments. By rapidly adjusting these surfaces, the missile can alter its trajectory, making it a nightmare for enemy air defenses. Adding another layer of complexity, some hypersonic missiles are designed to utilize what's known as boost glide technology. Instead of following a purely ballistic trajectory, these missiles are launched into the upper atmosphere on a powerful rocket. Once they reach a certain altitude and speed, they detach from the rocket and glide back towards their target, using their aerodynamic shape and control surfaces to maneuver through the atmosphere. This boost glide capability allows them to cover vast distances while maintaining their maneuverability, making them a true game changer in modern warfare. It's a competition driven by the understanding that hypersonic weapons have the potential to reshape the balance of power, rendering existing defense systems obsolete and creating new vulnerabilities. The United States, long a leader in military technology, is not alone in this pursuit. Russia and China have also invested heavily in hypersonic research and development, fielding their own arsenals of these game-changing weapons. This hypersonic arms race is reminiscent of the Cold War competition between the United States and the Soviet Union, but with a new set of complexities. The stakes are arguably higher, as hypersonic weapons compress the time for decision-making, increasing the risk of miscalculation or escalation. Moreover, the proliferation of hypersonic technology to other nations raises concerns about regional instability and the potential for these weapons to fall into the wrong hands. The race for hypersonic dominance is not just about building faster missiles. It's about developing countermeasures, new defensive technologies capable of detecting, tracking, and intercepting these incredibly fast and maneuverable weapons. It's a technological tug-of-war, with each breakthrough potentially shifting the balance of power. This competition is driving innovation at an unprecedented pace, pushing the boundaries of materials science, propulsion technology, and artificial intelligence. But it also raises profound questions about the future of warfare and the role of these weapons in an increasingly interconnected and volatile world. The United States has a long and storied history of pushing the boundaries of aerospace technology, and hypersonics is no exception. From the early days of the X-15 experimental aircraft to the development of the space shuttle, American scientists and engineers have consistently sought to conquer the challenges of high-speed flight. This legacy of innovation continues today, with the United States at the forefront of hypersonic research and development, investing billions of dollars and leveraging the expertise of its top research institutions and defense contractors. One area where the United States has made significant strides is in the development of advanced Scramjet engines. These engines, capable of operating efficiently at hypersonic speeds, are essential for powering long-range hypersonic missiles. American researchers have made breakthroughs in areas such as supersonic combustion, thermal management, and engine design, paving the way for the creation of scramjets that can sustain hypersonic flight for extended periods. Beyond propulsion, the United States has also made remarkable progress in developing materials capable of withstanding the extreme temperatures and pressures of hypersonic flight. These materials, often composed of exotic alloys and ceramic composites, are used to construct the heat shields, airframes, and other critical components of hypersonic vehicles. American researchers are at the cutting edge of materials science, constantly pushing the limits of what's possible to create materials that can endure the inferno of hypersonic flight. These technological advancements are not just theoretical, they are being translated into real-world capabilities. The United States has successfully tested a range of hypersonic vehicles, demonstrating the maturity of its technology and its commitment to maintaining a technological edge in this critical domain. The United States is not just researching hypersonic technology, it's actively developing and fielding a new generation of hypersonic weapons designed to maintain its military superiority in the 21st century. These weapons encompass a range of capabilities, from fast and maneuverable missiles to hypersonic glide vehicles capable of striking targets thousands of miles away. One of the most prominent examples is the AGM-183A ARW, or Air-Launched Rapid Response Weapon. This air-launched hypersonic missile, designed to be carried by strategic bombers such as the B-52 and B-1B, is intended to provide the United States with a prompt strike capability against high-value, time-critical targets. Another key program is the Hypersonic Conventional Strike Weapon, or HCSW, a ground-launched hypersonic missile designed to provide the U.S. Army with long-range precision strike capabilities. The HCSW is envisioned as a highly mobile system, capable of being rapidly deployed to different theaters of operation to deter adversaries or respond to emerging threats. In addition to missiles, the United States is also developing hypersonic glide vehicles such as the Common Hypersonic Glide Body, or CHGB. These vehicles, launched atop ballistic missiles, are designed to glide through the upper atmosphere at hypersonic speeds, maneuvering to evade enemy defenses and strike targets with pinpoint accuracy. The CHGB is intended to be a modular system capable of carrying a variety of payloads, including conventional explosives, electronic warfare systems, or even kinetic interceptors designed to destroy enemy missiles in flight. These hypersonic weapons represent a significant leap forward in military technology, providing the United States with new options for deterring adversaries, responding to crises, and maintaining its military edge in an increasingly complex and challenging security environment. The advent of hypersonic weapons has profound implications for global security, introducing new challenges to strategic stability and potentially altering the dynamics of international relations. One of the most pressing concerns is the potential for hypersonic weapons to compress decision-making timelines, increasing the risk of miscalculation or escalation, particularly in a crisis situation. The speed and maneuverability of these weapons leave little time for leaders to assess a threat, communicate, and make informed decisions, potentially leading to hasty actions with unintended consequences. Moreover, the proliferation of hypersonic technology to other nations raises concerns about regional instability and the potential for these weapons to fall into the wrong hands, including terrorist organizations or rogue states. The spread of hypersonic weapons could fuel regional arms races, as countries seek to acquire these capabilities to deter their adversaries or gain a military advantage. Another concern is the potential for hypersonic weapons to destabilize existing arms control agreements. Many of these agreements, negotiated during the Cold War, were designed to limit the number and capabilities of ballistic missiles. Hypersonic weapons, with their unique flight profiles and capabilities, blur the lines between ballistic and cruise missiles, potentially rendering these agreements obsolete or ineffective. The international community faces a significant challenge in addressing the security implications of hypersonic weapons. Dialogue, transparency, and confidence-building measures will be essential to mitigate the risks of miscalculation, prevent an unconstrained arms race, and ensure that these weapons do not undermine global stability. The pursuit of hypersonic technology is not just about building faster missiles. It's about pushing the boundaries of what's possible in aerospace engineering, unlocking new frontiers in high-speed flight, and shaping the future of warfare. As research and development continue, we can expect to see even faster, more maneuverable, and more sophisticated hypersonic weapons emerge, capable of striking targets with unprecedented speed and precision. But the story of hypersonics extends beyond weapons. The technologies being developed for hypersonic flight have the potential to revolutionize other areas, such as transportation, space exploration, and even commercial aviation. Imagine traveling from New York to London in under an hour or launching satellites into orbit at a fraction of the current cost. The quest for hypersonic dominance is driving innovation at an unprecedented pace, leading to breakthroughs in materials science, propulsion systems, and artificial intelligence. These advancements will have far-reaching implications not just for the future of warfare but for our world as a whole. As we venture further into the hypersonic age, one thing is certain: the future of speed is here, and it's moving faster than ever before. In the realm of modern warfare, where victory often hinges on split-second decisions and the ability to act decisively, hypersonic speed emerges as a game-changing tactical advantage. Imagine a battlefield where missiles streak through the sky at speeds exceeding 5 times the speed of sound, compressing response times and rendering traditional defenses nearly obsolete. That's the transformative potential of hypersonic weapons. Hypersonic speed fundamentally alters the dynamics of engagement, shifting the balance of power towards those who possess it. With their blistering velocity, hypersonic missiles can close vast distances in a matter of minutes, reducing the time adversaries have to react, reposition assets, or launch counterattacks. This ability to strike swiftly and decisively gives commanders a decisive edge in time-sensitive scenarios, such as preemptive strikes against enemy command and control centers, air defense systems, or critical infrastructure. By disrupting the enemy's ability to coordinate and respond effectively, hypersonic strikes can create chaos and confusion, potentially crippling their ability to wage war effectively. Furthermore, the speed of hypersonic weapons makes them incredibly difficult to intercept, overwhelming even the most sophisticated air defense systems. This combination of speed, range, and maneuverability makes hypersonic weapons a formidable force multiplier, capable of reshaping the battlefield in profound ways. For decades, nations have invested heavily in building sophisticated air defense systems designed to protect their airspace and strategic assets from aerial threats. These systems, often composed of a layered network of radars, surface-to-air missiles, and electronic countermeasures, have proven effective against traditional aircraft and even some ballistic missiles. However, the emergence of hypersonic weapons poses an entirely new challenge, one that could render these existing defenses woefully inadequate. Hypersonic missiles, traveling at speeds exceeding Mach 5, can overwhelm the tracking and engagement capabilities of most air defense radars. These radars, often designed to detect and track objects moving at subsonic or supersonic speeds, struggle to keep pace with the blistering velocity of hypersonic threats. By the time a hypersonic missile is detected and tracked, it may already be too late to intercept. Furthermore, the maneuverability of hypersonic missiles makes them incredibly difficult to target with conventional surface-to-air missiles. These interceptors, often reliant on predictable flight paths and longer engagement windows, struggle to hit a target that can change course rapidly and unpredictably. The combination of speed, maneuverability, and potentially low observable characteristics makes hypersonic weapons a nightmare scenario for air defense planners, forcing a fundamental reassessment of existing defenses and the development of new technologies and strategies to counter this emerging threat. In the realm of military strategy, the element of surprise can be a decisive factor, often determining the outcome of battles and even entire wars. Hypersonic weapons, with their incredible speed and ability to penetrate enemy defenses, introduce a new dimension to this concept, potentially giving the attacker an unprecedented advantage in the opening salvos of a conflict. Imagine a scenario where a nation, facing an imminent threat or seeking to gain the upper hand in a conflict, launches a preemptive strike using hypersonic missiles. These missiles, traveling at speeds exceeding Mach 5, would give the adversary little to no warning time, leaving them vulnerable to a devastating first blow. Targets that were once considered relatively secure, such as command and control centers, air bases, or missile silos, could be struck with pinpoint accuracy before any effective defensive measures could be taken. This ability to deliver a swift and crippling first strike could potentially paralyze an enemy's ability to wage war effectively, giving the attacker a decisive advantage from the outset. The potential for hypersonic weapons to enable such surprise attacks raises profound questions about strategic stability, the risk of miscalculation, and the potential for escalation in future conflicts. It also underscores the need for clear communication, confidence-building measures, and potentially new arms control agreements to manage the risks associated with these game-changing weapons. While the military applications of hypersonic technology are undeniable, the potential benefits of this revolutionary technology extend far beyond the battlefield. As research and development continue to advance, we can envision a future where hypersonic speeds transform various sectors, from space exploration and transportation to disaster relief and scientific research. One of the most promising applications lies in the realm of space exploration. Hypersonic spacecraft, capable of traveling at speeds exceeding Mach 5, could dramatically reduce travel times to other planets and celestial bodies, opening up new possibilities for human exploration and scientific discovery. Imagine reaching Mars in weeks instead of months, or exploring the outer solar system within a human lifetime. In the field of transportation, hypersonic aircraft hold the promise of revolutionizing air travel, Imagine boarding a plane in New York and arriving in Tokyo in under 2 hours, or traveling from London to Sydney in a matter of a few hours. While significant technical challenges remain, the development of safe, reliable, and commercially viable hypersonic passenger aircraft is no longer a far-fetched dream. Furthermore, hypersonic technology could be utilized for high-speed cargo delivery, enabling the rapid transport of goods, medical supplies, or humanitarian aid to remote or disaster-stricken areas. Imagine a world where vital supplies could be delivered anywhere on the planet within a matter of hours, potentially saving countless lives and alleviating suffering. The emergence of hypersonic weapons presents a profound strategic dilemma for nations around the world, forcing them to grapple with the challenge of balancing offensive and defensive capabilities in an era of unprecedented speed and technological advancement. On the one hand, the allure of hypersonic weapons with their ability to strike swiftly, decisively, and overcome existing defenses is undeniable. Nations seeking to deter adversaries, maintain military superiority, or simply keep pace in a rapidly evolving technological landscape may feel compelled to invest heavily in developing and acquiring these game-changing weapons. However, this pursuit of hypersonic dominance carries inherent risks. As more nations acquire these weapons, the potential for miscalculation, escalation, and even accidental conflict increases. The compressed decision-making timelines associated with hypersonic strikes, coupled with the potential for misinterpretation or false alarms, could lead to unintended consequences, potentially sparking a conflict that neither side desires. Therefore, the strategic imperative for the international community is to find ways to manage the risks posed by hypersonic weapons while harnessing their potential benefits. This requires a multifaceted approach involving dialogue, transparency, confidence-building measures, and potentially new arms control agreements that address the unique challenges posed by hypersonic technology. Across the globe, the pursuit of hypersonic weapons technology is not limited to a handful of powerful nations. It's a global endeavor, with countries around the world recognizing the strategic significance of this game-changing capability. While the United States, Russia, and China may be leading the pack, other nations are hot on their heels, eager to develop their own hypersonic arsenals or countermeasures. This global proliferation of hypersonic ambitions is fueled by a complex interplay of factors, including regional rivalries, national security concerns, and the desire to maintain a technological edge in an increasingly competitive international environment. For some countries, the pursuit of hypersonic weapons is driven by a desire to deter aggression from neighboring states or regional rivals. For others, it's about safeguarding strategic interests such as vital shipping lanes, energy resources, or overseas territories. And for some, it's simply about keeping pace with technological advancements, ensuring they are not left vulnerable in a world where hypersonic weapons are becoming increasingly commonplace. This global pursuit of hypersonic capabilities raises concerns about an unconstrained arms race, regional instability, and the potential for miscalculation or unintended escalation. It also highlights the need for international dialogue, transparency, and cooperation to manage the risks associated with these weapons and prevent a future where hypersonic dominance becomes a destabilizing force in international relations. China, a rising military power with global ambitions, has emerged as a formidable player in the hypersonic weapons arena, rapidly developing and fielding a range of advanced systems that have sent ripples of concern through defense establishments worldwide. China's hypersonic program, shrouded in secrecy, has made remarkable strides in recent years, fueled by significant investments in research and development, a robust industrial base, and a determination to challenge American military dominance in the Pacific region. One of China's most notable achievements is the DF-17, a medium-range ballistic missile believed to be capable of carrying a hypersonic glide vehicle. This system, first publicly unveiled during a military parade in 2019, has been described by U.S. intelligence officials as a game-changer, capable of evading existing missile defense systems and striking targets with high precision. Beyond the DF-17, China is also developing a range of other hypersonic systems, including hypersonic cruise missiles, air-launched hypersonic missiles, and even hypersonic anti-ship missiles. These weapons, if deployed operationally, could significantly enhance China's ability to project power in the region, target U.S. assets, and potentially alter the military balance of power in the Pacific. China's rapid progress in hypersonic weapons development has raised concerns about its intentions and the potential for these weapons to destabilize the region. The United States and its allies are closely monitoring China's hypersonic activities, seeking to develop countermeasures and maintain a credible deterrent against this emerging threat. Russia, under the leadership of Vladimir Putin, has made the development and deployment of hypersonic weapons a cornerstone of its military modernization strategy, viewing these systems as a way to restore its status as a global military power and counter what it perceives as Western encroachment. Russia's hypersonic program, with its roots in Soviet-era research, has gained significant momentum in recent years, resulting in the fielding of several operational hypersonic systems that have garnered international attention. One of Russia's most potent hypersonic weapons is the Avangard, a nuclear-capable hypersonic glide vehicle designed to be carried atop an intercontinental ballistic missile. Putin has boasted that the Avangard is virtually invulnerable to existing missile defense systems, claiming that it can maneuver at hypersonic speeds in the atmosphere, making it incredibly difficult to intercept. In addition to the Avangard, Russia has also fielded the Kinzhal, an air-launched hypersonic ballistic missile designed to be carried by MiG-31K interceptor aircraft. The Kinzhal, with its reported range of over 1,200 miles and ability to maneuver at hypersonic speeds, poses a significant threat to high-value targets, such as aircraft carriers, command centers, and infrastructure. Russia's assertive posture and willingness to deploy hypersonic weapons have raised concerns about the potential for miscalculation and escalation, particularly in the context of heightened tensions with NATO. The development and deployment of these weapons underscore Russia's determination to reassert itself as a major military power and reshape the strategic landscape. As hypersonic technology continues to proliferate, the world is rapidly moving towards a future where multiple nations possess these game-changing capabilities. This transition to a multipolar hypersonic landscape presents both opportunities and challenges, requiring a fundamental reassessment of existing security arrangements, arms control agreements, and the very nature of warfare itself. One of the most pressing challenges is the need to prevent an unconstrained arms race, where nations, fearing vulnerability or seeking a strategic advantage, engage in a perpetual cycle of hypersonic weapons development and deployment. Such a scenario could lead to heightened tensions, increased military spending, and an elevated risk of miscalculation or accidental conflict. International cooperation and dialogue will be crucial to establishing norms of responsible behavior, building confidence, and mitigating the risks associated with these weapons. This includes sharing information about hypersonic programs, developing codes of conduct for their testing and deployment, and exploring potential arms control agreements that address the unique challenges posed by hypersonic technology. While the challenges are significant, the emergence of hypersonic technology also presents opportunities for international collaboration. Nations, recognizing the shared risks and potential benefits of this technology, could work together to develop common standards, share research and development costs, and explore peaceful applications of hypersonic technology, such as high-speed transportation or space exploration. The future of hypersonic technology is not predetermined. It will be shaped by the choices nations make today and their willingness to work together to ensure that this powerful technology serves the interests of peace and security for all. We've journeyed from the earliest ballistic missiles to the cutting edge of hypersonic technology, witnessing a relentless pursuit of speed that's reshaping the landscape of modern warfare. The development and proliferation of hypersonic weapons signal a paradigm shift in strategic competition, one where the balance of power hinges on the ability to act decisively, strike with precision, and overcome even the most sophisticated defenses. The United States, with its legacy of innovation and technological prowess, stands at a crossroads. Embracing the hypersonic imperative means not only advancing our own capabilities, but also navigating the complex geopolitical challenges posed by this new era of warfare. The hypersonic arms race is not just about building faster missiles, it's about maintaining a credible deterrent, ensuring our ability to respond to threats, and protecting our interests in an increasingly volatile world. It's about staying ahead of the curve, anticipating the moves of our adversaries, and developing countermeasures that can keep pace with their advancements. This requires sustained investment in research and development, a commitment to innovation, and a willingness to adapt our military strategies to the realities of hypersonic warfare. But technological superiority alone is not enough. We must also engage in dialogue with other nations, seeking to establish norms of responsible behavior, build confidence, and prevent an unconstrained arms race. This includes sharing information about hypersonic programs, developing codes of conduct for their testing and deployment, and exploring potential arms control agreements that address the unique challenges posed by hypersonic technology. The proliferation of hypersonic weapons presents a profound challenge to global security, one that demands a concerted and cooperative response from the international community. The speed, maneuverability, and potential for surprise attacks associated with these weapons create a heightened risk of miscalculation, escalation, and unintended conflict. In a world where hypersonic missiles can traverse continents in minutes, the time for diplomacy and dialogue is now, before these weapons erode strategic stability and increase the likelihood of devastating conflict. Open and transparent communication channels between nations are essential to reducing the risk of misperception or miscalculation. Sharing information about hypersonic programs, conducting joint exercises to demonstrate capabilities and limitations, and establishing clear protocols for communication during crisis situations can help build trust, reduce tensions, and prevent misunderstandings that could escalate into conflict. Furthermore, the international community must work together to establish norms of responsible behavior for the development, testing, and deployment of hypersonic weapons. This includes agreeing on limitations for the range, payload, and targeting of these weapons, as well as establishing clear guidelines for their use in accordance with international law. The development and deployment of hypersonic weapons present a complex and multifaceted challenge, but it is not an insurmountable one. Through dialogue, cooperation, and a shared commitment to peace and security, the international community can navigate the challenges of this new era and ensure that hypersonic technology does not become a catalyst for conflict, but rather a force for stability and progress. While the military applications of hypersonic technology dominate current discussions, the potential benefits of this revolutionary technology extend far beyond the battlefield. As research and development efforts continue to push the boundaries of speed and endurance, we can envision a future where hypersonic technology transforms various sectors, from transportation and space exploration to disaster relief and scientific research. Imagine a world where hypersonic passenger aircraft could whisk travelers across continents in a fraction of the time it currently takes, revolutionizing air travel and shrinking the globe. Imagine the possibilities for space exploration, with hypersonic spacecraft enabling faster and more efficient missions to other planets and celestial bodies, expanding our understanding of the universe and our place within it. Hypersonic technology also holds immense potential for advancing scientific research. Hypersonic wind tunnels capable of replicating the extreme conditions of hypersonic flight could facilitate breakthroughs in materials science, aerodynamics, and propulsion systems. These advancements could lead to the development of new materials capable of withstanding extreme temperatures and pressures, more efficient and environmentally friendly engines, and novel aircraft designs that revolutionize air travel. The future of hypersonic technology is brimming with possibilities, both in terms of its military applications and its potential to benefit humanity in countless ways. As we venture further into this uncharted territory, it is our collective responsibility to harness this transformative technology wisely, ensuring that it serves the interests of peace, progress, and the betterment of humankind. As we've explored the fascinating world of hypersonic technology, one thing remains abundantly clear. The quest for knowledge, innovation, and pushing the boundaries of what's possible is fundamental to human progress. The development of hypersonic weapons is just one example of the incredible feats we can achieve when we dare to dream big, embrace challenges, and relentlessly pursue scientific and technological advancements. But our journey of discovery doesn't end here. The world is full of mysteries waiting to be unraveled, challenges waiting to be overcome, and innovations waiting to be born. Whether it's exploring the vastness of space, unlocking the secrets of the human brain, or developing sustainable energy solutions for a brighter future, the possibilities are limitless. Stay curious, my friends. Never stop questioning, exploring, and seeking answers to the unknown. Embrace the power of education. Delve into the exciting world of STEM, and who knows? Maybe you'll be the one to make the next groundbreaking discovery, invent the next revolutionary technology, or inspire future generations to reach for the stars. The future belongs to the curious, the innovators, the dreamers who dare to venture beyond the horizon of what's known and explore the infinite possibilities that lie ahead. And as always, keep looking up. Don't forget to subscribe for more fascinating journeys into the world of science, technology, and the cosmos. Until next time, stay curious, stay informed, and never stop exploring the wonders of our universe.